All right, continue to layer it in. We're going to continue this sequence. Right now we're on number 2. How do you analyze the interaction between objects? Make things happen, make electric current happen. There's 2 main ways that you're going to use. And that's going to be, we're going to talk about fields, which tends to be very abstract, just like electric charge is abstract, or mass is abstract for people, and forces. We can also, so that would be doing a force analysis or field analysis. I'll tell you generally how the distinction. And we can also do an energy analysis. So we can talk about potential energy or potential. So let's clarify these distinctions here, and then we'll move on to the electric field and electric force, electric potential energy. Right? Okay, cool. Let's do this. So the question is electric and magnetic interactions. We want to get the concepts now, and then you'll be able to do the quantitative math analysis. If you can add up vectors, you're good. And if you know the definition of potential energy, change of potential energy, it's the negative work done by a conservative force. We'll get into that more again. Just let it roll over you. The big question here is, how does one object push or pull another object without touching? And we can address that for gravity, for the electric, and for the magnetic forces. It's pretty weird. I mean, it really is weird. We get so used to it. When you're used to it, you forget to notice that this is really weird. Of course, if you sat around noticing that it's weird, you might not get anywhere, you might starve. But that is weird. And in fact, when Newton was asked about that, he basically said, I make no hypotheses. I don't know, it just does. Clearly, Earth is going around the sun. It's not going in a straight line, it's turning. There's got to be a force to make it turn. Who are you going to blame it on? You're going to blame it on the sun. Then he came up with a law, a mathematical law, 1 over r squared. Gravitational constant, the mass of sun times the mass of Earth, divided by the distance between the centers, squared. Does really well to explain the motion of the planets. It matched Kepler's laws. It was great. Turns out, when you get closer to the sun, gravity is a little stronger, and Mercury, the closest planet, deviates noticeably, just a bit. So Einstein had to come up with another idea of warp space-time. We're not going to go there. But again, the question still remains is, how can Earth, gravities, we're so used to them, we think that they fall because, just as Aristotle did, they fall because they want to fall. No, they're somehow being pulled, or something is happening right here that makes them go that way. So it's weird. So too with electrical stuff, you can rub, right, fur or hair, and you can lift stuff. You can make things happen electrically. You can, magnets obviously are just so cool, right? So how does that happen? I mean, that is just bizarre. How does that push or pull and move things around without touching, move a compass around, etc.? So we're going to come up with some ideas, not worry about how it works, but whether or not they even exist. But you'll find out they do take on a life of their own. Very powerful, again, very abstract. So, remind you, electric charge. Initially, people didn't know what it meant. It just meant you rubbed it and it had this electrical interaction. And they didn't know why. Then they found out about atoms and electrons. Oh, I get more electrons or less electrons, etc. So that's what charge is, and if you have more charge, then you either gain more electrons or lost more electrons, as a common example. Now we've got this idea of fields, again, very abstract, and potential. So let me talk about them. For gravity, for the electric, and for the magnetic force. So here's how we talk about it. These 2 objects have mass. We know that mass plays 2 roles. It's inertia or resistance to acceleration. We also know that it's responsible for gravity. Right? So the objects, these aren't masses, they're objects, and one of the properties they have is mass. they attract each other somehow, very slightly. It's incredibly difficult to measure that attraction, but they are attracting each other with mass, and they're spherical. Fine. Well, how can they pull on each other? Or again, more obviously, how can Earth pull my keys? We say that one object is creating a field. It's putting out something. It's like it's calling out. If no one's listening in the room and I talk, I can put out a field of sound. If someone's there, then that field can be, the sound can be received, and I could say, hey, could you come here? Or hey, could you go away? And then, how they interact, I could say, come here, and they could go away, or I could say, go away, and they could come here, if they're a particularly negative person. Yeah, it's going to go that way. But if they're a positive person, I say, could you go away, they would, and if they say, could come here, they would. Okay, that's going to be good. We'll get to those details later. Anyway, it's a weird thing. So what a field is something that has an amount. You can think of it as a strength, but it's not quite force, so you have to be really careful as you're learning this. Don't overthink the why of it, just go with it. But it's something that has a value, a magnitude of a field at every place in the room. So if I went around this room and measured the temperature, there would be a field of temperature. And that would be a scalar field, because temperature doesn't have a direction. But at every position in space, and you can do space and time, but every position there is a value. I could take a rod and I could heat it on one end. And so the temperature could vary along here. And the rate at which it varies, talk about a gradient, things like that. But there would be a field of temperature values. Sound, how loud the sound is from my voice, it has a value. So you could put a receiver or a detector at different places in the room. So it has that value. Light, how much light is received at different places in the room from a bulb. And so that's what we're talking about. Something creates the field. So I'm going to put this up here, and you're going to use it a lot, so you'll get used to it. And remember to go with things, think about them, come back to them. And it's only like the fourth time or whatever that you come back, and then when you go back and tutor it, that you really get it. But a field is created by what I call a source. One book, I think it's Knight, calls it an agent. I like that too, an agent. Something that makes the field. I am making a sound field. A light bulb is making a light field, whatever that is. Now a force is felt by, so if I make a sound field and there's a person with ears, they can hear, then that's felt by, they feel the field that's created by the source. This is important. So the source creates a field of, say, sound. There's no force because there's no one there. But when there is someone there, wherever they are, they'll get the field that's there. Right? If I hold up this pen and people are sitting in this room, they'll see light beams that hit their eyeballs. If I make a sound field, they'll hear the sound, the vibration that reaches their ears, that's at their ears. So there is a value for the sound at different locations, created by the source. The source creates a field. It has a value all over the place, but it's felt by an object that can receive that field, and it receives the field wherever it is. So if someone is deaf, or someone, or something doesn't have, like this, doesn't have ears, I can't say, come here, So if it doesn't have ears, it can't respond to the sound field that's at that location. Come here, red pen. Come here, green pen. They're each getting vibrations. And you can actually measure that. They're each getting vibrations. But they don't respond because they don't have the property necessary to respond to sound, namely ears. So let me put this in. So a force is felt by, what color shall we do? Felt by, or experienced by, or received by I like the word receive. The sound is received, and you will receive the vibration wherever you are that's at that place. Received by I like to call it, well, a receiver. Stereo receiver, whatever. It's a receiver. So I like to call, that's my terminology, call it whatever. Felt by a receiver. They get the force from the field where the receiver, I like to use R, is at that location, right? Think sound, it's a really good analogy. It's going to apply. So even if you're sitting next to someone, they're getting a little different, they're getting the vibration here, your right eye's here, your right ear, left ear. The other person gets this vibration. Right, wherever you are, you're getting that field. So the location's important. And that was created by whom? The source. Whoever's, in this case, speaking or whatever it is. Created by the source, which I like to use S, or the agent, that which created that field. If that makes sense, then we can use that type of thinking, whether it's real or not, we can use that type of thinking to analyze gravity, electric, and magnetic. And we're going to take that same concept and put it into energy as well. So here we go. So gravity field, that means that we know that mass creates gravity, but small mass, like yourself, objects around you, don't create much gravity. Of course, the major gravity is Earth. If you go to Moon, then you pull 1/6 as much on the surface. Mars, 1/3 as much on the surface. So gravity, for example, the field, sometimes called gravity field. Sometimes we use the kind of a script G. And it's created, oh, I've done a horrible thing, sorry. I'm talking about fields. Gotta do the right color here. It is green, but let's see red. So, a gravity field. So Newton didn't have this idea. Newton didn't. Okay, Faraday, Michael Faraday, over this idea applying down here, that we create this field, it creates gravity field created by, say, Earth or Sun or whatever. So the sun is creating a gravity field. And wherever you are, or your planet, the planet is, it will feel gravity. So, for example, Mercury's in closer, it'll feel a stronger field there. then Venus is a weaker field because it's farther from the sun. And in fact, it gets weaker as 1 over the distance squared, 1 over r squared. Earth feels a weaker field, Mars feels weaker, Jupiter feels a much weaker gravity field, but the field is there. And so, if I have, let's say this is the sun, and this is a planet going around it, and here, it's this green sun is creating a field of gravity everywhere, but there's no force. There's no force unless you put something there. So we're going to calculate the field so that we know when we put something there what the force will be. The stronger the field, the stronger the force. The weaker the field, the weaker the force. But also, the more stuff we put there, if it's pulling on ball number 1, or A, let's call it A, and ball B, then it pulls on the combination with more force. So it depends on where you are and what the field strength and direction is at any place, and how much of the property you have to receive it is, in the case of gravity, mass. Okay. So the force, stick with our force, F, either lowercase or capital G, doesn't matter, force of gravity, is always a pull. And it's a pull towards the source. So there's a direction, my vector. The source of the field. Again, if you have a stronger field, you'll get a stronger force. Does that make sense? What's responsible? What's the property that makes gravity happen? It's good old mass. So this is a little different. With sound, I need vocal cords, say, to create it. But to receive it, I need ears. My vocal cords don't receive the sound unless you feel the vibration. So you need the sound. With gravity, you need mass to create a field. I'm creating a gravity field. It's very weak, and you probably can't even measure it. It's so weak. Earth is creating a gravity field. It's got a strength here. It's got a strength here. There's no force, except for the air there, which does experience it. But when I put something there, there's a field. Right? There's a field and a force. Now there's just a field. Does this make sense? There's a field everywhere, and I can talk about it. But I'm only interested, probably, in the field at the place that I'm going to experience a force. If you have that idea, you're in really good shape for the strange world of electric and magnetic interactions. So mass creates a field, and when an object with mass is at some place where there's a field, it will experience a force that has a strength dependent on how strong the field is there and how much mass the receiver has. As you know, things with a small amount of mass get pulled down weaker than things with more mass. And things with more mass get pulled down more. They experience a greater force. Okay, now we can go. So, we're used to doing force analysis. We still do. Remember, we add up all the forces: friction, tension, spring, normal force, hand, whatever forces you've got, gravity. And electric force you can put in there. That's the good news. Magnetic force, you put it in there. You just do force analysis. It all applies, right? So that's cool. F equals ma, but it's the net force on your receiver. right? Causes, and M is still working. M is the inertia. It's still there. Even if you're not worrying about the gravitational force, it's all electric and magnetic. You still got inertia playing in there. All right, cool. Let's continue on here. Let's go down this way. Electric. So if something is charged up, electrically charged, I rub something, and it becomes electrically charged, then it puts out a field. And so it has values and direction, an amount and a direction everywhere in space. Now I might want to know how much it is everywhere in space and write an equation for it, so that if I put something here, I could find out what the force is. Is it going to push away or is it going to pull toward? So electric and magnetic forces add a new level of complexity. Gravity always attracts. But now we got plus and minus. We got attraction and repulsion when it comes to the electric. And we'll see magnetic is kind of weird too. So we'll get into that as a deflection. So, what creates and feels electric force? That weird property called electric charge. And if you have more electric charge, you're going to create a stronger electric field around you. Right? If someone's wearing more perfume, they create more of an aroma field around them. Right? At different places, is it going to smell more or less? And what do we use for that? We often either use a lowercase q, kind of like quantity, or an uppercase q. It's not a vector, so I don't have vectors. Obviously, with mass, I use a lowercase m or a capital M. That's what creates gravity. Why does an electron have charge? We're not going there. It just does, right? Why does an object? Probably because it has more or less electrons than protons. Okay. So what do we say? We charge something up, we rub it. Right, here it is. It's got an electric field all around it. And we can calculate it. That electric field we write as E from some source, or let's write it this way. How about from Q source, the charge of the source, at wherever. That's the electric field, strength and direction. We can get more into that next time. So a force will feel, so it's like saying, well, Q, the source isn't reaching out and touching it. It isn't pushing it away or pulling it. I'm not reaching out and grabbing that person, pulling or pushing them away. I'm creating a field which communicates to them. So don't overthink this, but this is how we do it. So a charged object will have a field, a value, and a direction in all places around it. And if you have another object which has a net electric charge, whether it be an electron, a proton, an ion, an object, whatever it is, then you have force electric, often we do E or EL, is going to be from the electric field at the receiver and the receiver has charge QR, uppercase or lowercase. And that force is going to be, so that's that, on that receiver's electric charge. And if you've got more electric charge, you're going to feel more push or pull. And if the source has more electric field, Electric charge, it'll create a stronger field. So it's kind of this intermediary, right? I can create louder sound, and then the sound that you hear will be louder. But how loud it is depends on where you are, and then have that effect. All right. So hopefully that makes some sense. We'll get into that more in a bit. That's the idea. So two, you have a magnetic source that creates a magnetic field. Now this is going to be a little weird, a little less obvious. The magnetic field is giving a letter B. And maybe it's from a fellow named Biot, B-I-O-T, French. B is the magnetic field. We got too many M's. Although you use capital M with a vector inside of materials when you do more advanced. So, whatever, letters, right? It doesn't matter. But B, and again, from the source, let's talk about that, at some place. So there's as with any vector, there's an amount. It's not a force. These are not forces. These are not newtons. But it's got a strength and an amount. And it's got a direction. That's what you have to learn. There's a lot of details to still be learned at that place. Now, what's the source? And what would be required to feel that? So I could have done that in red, too. But just getting a little red in there. Okay. Well, you have to put something in that field. But it's got to be something with ears that can hear the sound field, with mass that can hear the gravity field, with electric charge that can feel the electric field. So what is that property? Length is a little tricky, so you're going to get used to it. Turns out there's going to be three kind of properties. There is moving electric charge. So I'm going to do this a couple ways. There's the charge, how much charge, how many coulombs, often, and its speed and its direction. And you're going to see later, or moving charge through that wire, which is the electric current times the length and direction of that wire. So I'm going to put those two together. And then there's magnets, which are the most common and obvious thing that you see, and yet, really fundamentally, the most, I don't know, they're all kind of profound and deep, but this is a quantum mechanic effect. So it's kind of weird, but you can talk about magnets pretty easily. So, a magnet can push and pull another magnet. But so can moving electric charged objects. A beam, remember the beam? Or the electric current can create a magnetic field, and then if you put that in the field, wherever you put it, however strong that field is, you'll get a what? That's right, a force magnetic. So now what I call it, a force B, a force M, call it what you want. Use whatever your textbook. People use different things. But it's a magnetic force from the magnetic field at the receiver on whatever it is. The charge and motion of the receiver, or the current and length of the wire. And that's how we're going to do it. But again, remember, forces obey Newton's laws. Until they don't, but they do for most things. So, okay, so we can just do Newton's laws. That's it. Now, Newton's laws can be a little bit harder to use, and if you have lots of interactions, we know that energy is a better way, or an easier, more effective way to analyze things often. Energy is sort of the go-to method for analyzing stuff. It's very, very useful. And so we can talk about energy. Hi. All right, I know this is a lot. Let me just say this, and again, we'll come back to it. We talk about two concepts in a similar way. We talk about potential energy and potential. One of the more abstract, again, where we have really abstract electric charge, fields, and potential. If you've got that, you're good to go. Then we'll get into electric flux and magnetic flux, electric flux and magnetic flux, electric field density and magnetic field density, and energy density. So a few more weird things. You get used to them. But go with it, because you know it works. All right, so what is this? Potential energy. This is the potential for kinetic energy that an object R has, the receiver has. Why does this have potential energy? Why does this have an ability to hurt me? Because Earth is pulling on it. So I'm really saying what I said over here, just a different way. Remember how we turned Newton's laws into energy? So this does give me another way. It's a very nice way to analyze it. That's the real point. That's the way to think about it. The reason, if Earth stopped pulling, I could let it go and it would just sit there by Newton's laws. Also, we know that gravity is a conservative force. If it slows things down, it will speed it back up if you let it just be on its own. So the receiver has potential for kinetic energy. Potential for kinetic energy that an object R has because of the force from the source. Again, just keep moving. You don't have to be clear on this right now to go forward and then come back. Potential then, what is potential? Okay, I'm going to say it the way that I like to say it. I like to say this. I like to say potential now potential energy, maybe I'll write that. Potential energy is the potential for kinetic energy. So potential energy is the potential for kinetic energy. I got more potential for kinetic energy. I got more potential for kinetic energy, which is more potential for ouch. Potential is the, this isn't going to make sense, is the potential for potential energy. So, I know it's weird. And you use this all the time. You ever see a battery? Oh, volts. How many volts is that? Volts. That's potential. That's electric potential. Volts. That's what we're talking about. Electricians use it all the time. They do a good job. They don't have this theory behind them, and they don't need to do the wiring. But potential, volts, is the potential for potential energy. That's how it works into the theoretical framework, the mathematical structure that we move around and calculate. So let's do gravity. All right, for gravity, I can say, I can look at gravity, I can look at shelves. Think of shelves. Earth is pulling down with the force of gravity, only if something is there. Otherwise, there's a field. I can just as well talk about, instead of forces and fields, I can say that there's a potential. If I have shelves for gravity, and these are shelves, then I would say that there is higher potential, even with nothing on the shelf, no receiver. That's because Earth is pulling down, so here's the ground. And we do use ground in electric stuff, you might have heard that. Higher potential, and this is lower potential. But there's no potential energy if there's nothing on your shelves. So you have to put something there. I know maybe this is abstract, right? So let's do this. So I'm going to take this over here, and we're going to put something on the shelves. Here's the ground. Okay? And we say, oh, if I put a bowling ball somewhere, it would probably be bad to store my bowling ball up here. Why? Because it's got more potential energy to hurt me or the cat or whatever it falls on, right? Here it would have less potential energy. And remember that we use the letter U often for potential energy? Capital U for potential energy. So we'd say the potential energy, we'd have more potential energy of gravity, and we'd have less potential energy of gravity. And at some place we call it zero, but we can call zero wherever we want, because we could say that's zero until you dig a hole and you go, oops, it fell in. Okay? So you get to choose where zero is. This could be zero, and then this would be negative. Remember that. Now, how much potential energy I have depends on what I put there. I've been shocked by close to 1,000,000 volts. Feels like a rubber band snapped. No big deal. I've been shocked by 120, and it was not good. So what matters is not how far something falls only. It's also what falls on you. If you take a little ping pong ball, less mass, less potential energy. So, probably losing you. Good thing you can hit balls. How much potential energy I have depends on the potential created by the source, here Earth, and how much the thing has that I put there. Right? Just go. We're going to use the same thing with electric, but it gets a little weird because, again, it can push and pull. All right, so let me just say this and we'll get to this in more detail. Okay, so you've got an electric potential. This is weird. V from a charged source. And just like from Earth, there's potential everywhere. You can have, it has got potential everywhere. I'm going to leave it there. Leave it there. It happens to have units of volts, so they have the same letter, which is unusual. Force has units of Newton, so F and N, but here, U and V. And if I put something there, it's the same as this idea. If I put something there, it'll have potential energy. If nothing's there, I just have potential. So, U electric from that potential at the receiver, and we often say the potential energy of the receiver, or let me say it this way, so of the electrically charged receiver. So the potential energy depends on the potential and how much you put at that potential. The potential is created from the source. Kind of crazy, that's what it says. But you'll be doing this over and over. Once you get this, you start doing the math and you look at the geometry. So the charged object creates potential. Earth creates potential, shelves. If you put nothing there, you've got potential. If you don't do any work, you've got potential to be a great engineer, but you don't do any work, and that's never going to go anywhere. So if you do the work, then you've got an ability to do something. You've got energy. Here, you've got potential energy you put towards it. Now, I want to point out that, and this is important, little preview, this is quick, is that with magnetism, it's a little bit odd. And so for now, we won't get into this. Okay? So not for magnetism. And I'll say now, and many of you will never go to this place of a vector potential. It's a weird thing. So just so you know where you're going, you're not going to be getting into that. You'll be looking more at magnetic forces. And so that's the weird and wild world of thinking about how we talk and think about and quantitatively analyze pushes and pulls from things that aren't even touching. We can do a force analysis, but the force is from the field there. We can just look at the field and not put anything there. Or we can do an energy analysis, and we can look at the potential energy of the thing there. Or just the potential field. We really call that a potential field because the potential has values everywhere. I've got gravitational potential everywhere. When I put something there, it's got gravitational potential energy. If I put something more there, it's got more gravitational potential energy, right? That's it. Potential energy is the potential for kinetic energy. More. Potential is the potential for potential energy. I know, it's crazy. Think of it as shelves. The higher the shelf, the more potential energy you can get. But the more you put there, the more potential energy you get. Ping pong ball versus a bowling ball. So too with electric fields, creating electric potential. And the more charge the object has that you put there, the more potential energy it will have. So we're going to go back more. That's the challenge. It's your first challenge with this conceptual stuff. And then you'll make it a little more concrete and do some circuit examples using the idea of volts and potential in a fairly simple way. So it's sort of unfortunate we have to start off with a very these abstract ideas and a little more math, and then you back off and do some simple batteries and wires and resistors. And then we kind of do that. We keep layering in, do a little magnetism, then put in some circuits, and then see the connection between electricity and magnetism, which is wild. And I'll just say one more thing in general, now that I have these two up, electric and magnetic, is that when Faraday came up with this idea, like, well, how does one thing push or pull without touching? Well, maybe it puts out something, a sound field, that has an effect on the object that's there. And it puts out stuff that's everywhere, but it has an effect based on what the value is there. Made up. Is it real? It works. Mathematically, it works. However, I'll give you a little bit of a punchline of the course, too. As people explored in the 1800s, how strong, what direction is the field, the force, the potential energy? How strong in what direction for magnetic? They found that these two affected each other. And the changing electric field makes a magnetic field, and changing magnetic field makes an electric field. And they go, one goes this way and the other goes that way, and they travel off as a wave, creating themselves at the speed of light. And so it has a deep connection, leads to relativity. Very cool. It's worth your hard effort. Your head's going to hurt. When your head hurts, you put it aside and you come back and you put it aside. Okay, enough said. We'll do electric stuff and get in with the electric stuff as our first step into this wild world.